Let us now discuss the philosophy behind the FIR digital filter design. Okay, FIR filter design. So basically, it is not a completely analytic method. So we have to start with the specifications. What are the specifications of a filter? What we aim and what is the idea to achieve that aim? We assume that the transfer function of FIR digital filter design follow the ideal filter response. What is ideal filter response? So for a low pass filter, the ideal filter response is this. If this is omega, the frequency, and this is, let us suppose, this is digital filter impulse response, like this, mod. Okay, digital filter impulse response of digital filter, then ideally it should have this behavior. Agree? Ideally it should have an ideal filter. When we discussed the ideal filters, we told you that ideally a filter should have a selectivity, a smooth selectivity for the frequencies less than omega c, or a complete rejection, that is zero rejection beyond the omega c. Okay? So that we can say that if omega p is the pass frequency, then it is a there is a sharp demarcation between pass band and the stop band. Okay, so this is what the ideal filter will have the response. Okay, so ideally what should be HD? So ideally HD should be HD e raised to power j omega. It should be equal to e raised to power minus j omega tau and 0, when mod of omega is in between omega p and pi. Okay, and 0 otherwise. It means that, so what is its mode? Its mode is 1 when omega is in between omega p and pi. Its mode is 1 when omega p is between omega p and 1. So if this ideal filter response have to be realized by using a finite impulse response, so what will be HD? It will be summation n changing. Ideally it should be having infinite terms. Yani HD. This is the frequency Fourier series. This is the Fourier series for this. This is the Fourier series for impulse response. Okay? Because it is in the frequency domain. So if it is in n domain, then it can be written like this. If this Fourier series has infinite number of terms, but infinite number of terms give rise to IIR filter design. Okay, infinite number of terms gives rise to IIR filter design. So we arbitrarily truncate it to 2m plus 1 number of terms, like this. Let us say this is finite in length. Okay, m minus m to m, so that this truncation is due to the fact that HDN is finite. We are assuming HDN to be finite, and we are assuming it to be finite of length 2m plus 1. 2m plus 1 arbitrarily. We have assumed this. Okay. So it will be having a zero phase. Why? Because there are number of terms in the positive side and the negative side. It means e raised to power minus j and omega term will be there, and e raised to power plus j and omega terms will be there. So they will be added together and they will be giving a zero phase term like sine and cosine. So these zero phase filters is not realizable as it will be a non-causal filter. So it requires HD to be 0 for all n values of. We require HD n to be 0 for all values of n less than 0, because we need to make a causal system and only causal systems are realizable. Therefore, we will assume HD to be 0 for all values of n less than 0, so that HD will be equal to e raised to power j omega equal to approximately, of course, approximately if it has finite number of terms, then it will be having, this can be approximated to this hn e raised to power minus j n omega. Okay, because we have to make it a causal system. Okay, so as if infinite length impulse response is allowed to pass through a window of rectangular shape, we can write it as let us suppose this is the approximated transfer function of a finite length filter. Okay, what is basically our assumption? Our assumption is that since a filter will have infinite terms, this is a Fourier series representation of a filter, it will have infinite terms, but due to finite, we have assumed the impulse response to be finite, so that we can truncate it to 2m plus 1 number of terms, so that this infinite Fourier series can be approximated to a finite number of terms. Okay, 2m plus 1, and because we have to realize it, so it has to be causal, and for causal system we require HD to n to be 0 for all n less than 0. So we approximated it to n changing 0 to n minus 1, that is positive number of terms. So HD will be having a causal number of terms. It means HD is a causal system, and so this discussion can be approximated to this function Wn. Wn is called window function, which is equal to which is basically equal to 1 and 0 when n is in between 0 to n minus 1, n minus 1 and 0 otherwise. 0 otherwise. Okay. So we can approximate a impulse response of the filter by using this expression, where this expression approximate HDN. The HDN is the impulse response of the digital filter, by multiplying it to a window function Wn, which have this kind of a behavior. Mathematically, Wn can be written like this, and this is called a rectangular window. This is basically a rectangular window. And this technique is called windowing. This technique is called windowing. So it has basically some difficulties also, because windowing means we are defining it to be like this, function to be like this, Wn, but since there is no sharp changes, so there can be a ripples here and here. So this is the practical difficulty. There can be ripples due to Gibbs phenomena. Gibbs phenomena we studied in last semester. So whenever there is a sharp change, there will be some oscillations near the point of discontinuity, and it suffers this practical limitation. The rectangular window suffers this practical limitations. So the idea is to optimize this Wn, rectangular window. We generally optimize this rectangular window by different functions, and based on these different functions we will having different types of digital filter design. Windowing functions are different. This is the simplest approximation, rectangular window, but this rectangular window is modified by different inventors, different designers, engineers, and we will be having a complex kind of a window. But basically our aim is to design a digital filter by using under this mathematical transformation, where HD, that is the digital filter impulse response, is approximated to this kind of expression, where windowing function is used to obtain the finite length impulse response. Okay, so there are different windows functions which are given in the book. For example, this is rectangular window. Rectangular window is this. Okay, there could be a modified rectangular window. Where what we do is we make first term and last term as half, and rest of the terms here as 1. This is called modified rectangular window. Where the first term, that is 0 पे half है, और n minus 1 पे half है, और यहाँ पे सब 1 है. So this is one example. Another example is hand window, where Wn is defined as half 1 minus cos 2 pi by n divided by n minus 1, when it is in between 0 to n minus 1 and 0 otherwise. This is called hand window.